So I wanted to quickly get something a bit more concrete and visual, because this is too much formulae. And so I'm just looking at this setosa.io about eigenvectors and eigenvalues. So this is just a quick visual. So we will come back to these concepts again, not just through linear algebra. We'll come back at it through GraphX, which is this vertex programming framework in Spark. And in fact, even Google's PageRank algorithm, which essentially is directly related to the eigenvector of a so-called Markov matrix representation of all the web pages in the world. And Google exists mainly due to this algorithm initially, right? So does everyone know what a Markov chain is? Okay. Okay, you don't. Right. Okay, it doesn't matter. These are all just words, right? So we'll go through this thing again. It's important to have conceptual understanding. So what this is just two vectors, A1 and A2. I can change them here, and you can see the values changing. This is what I meant by the matrix A is seen as two vectors, a blue vector and a green vector as the columns, right? So if I change this, you see I'm changing the entries here. Now, so generally that's the normal way to see a matrix A as column vectors. Now what I'm taking is, I'm interested in A times V. So if I took some other arbitrary vector V, right? So let's say V is, V is now close to say 1, 1 or something, right? So that's 1, 1 where V is going from 0, 0 to this point. Okay, so that's V. So now what I'm interested in A multiplied by V, right? So A times V comes from, hitting these columns with each coordinate of V and then doing the sum. So this is now A times V. So there's some sort of meaning to it. Of course, if I change A, AV changes, right? XV. Okay. This is what I was blabbering before by like columns of matrix and so on. So you have some simple thing like this. So lambda is called the eigenvalue and V is called the eigenvector when something special happens. So that is when so when A times V is just some constant lambda times V, right? So there are some special places that V can be, so that something like this maybe, so that all you have to do is A times V will be some little elongation of V, some factor multiplied by V. So if you have that situation, then we say V is an eigenvector of A and the factor that you multiply by V to get A times V, that's called eigenvector.
Yes.
Yeah.
So one of the easiest and best explanation about this.
Yeah. So here's the one.
Values.
Yeah.
I heard it's like usually when you apply some sort of metrics on your vector either changes in length or in its orientation, things like this, it changes somehow.
Yeah.
And there are some special vectors on which you apply this matrix and they don't rotate.
Yeah, I think that's kind of this, right? This is now like
geometrical interpretation.
Yeah, that's exactly. Yeah, I think that's so. This is concretely. I don't think the animation will work for S2, which is sort of. So everything along this S1 is called the eigenspace. The first eigenspace. So if V is along this eigenspace, if that's an eigenvector, you see A times V is just some factor multiplied by V. It still remains there. Right? This is, I think. Anyway, so these are eigenvalues and eigenvectors and eigenspaces and so on. So I think I can change this. So now my eigenspace has changed. So of course, if V is over here, which is not an eigenvector, then A times V is it's not going in the same direction as V, right? But if I bring V to this eigenspace, now you see A times V, as long as I move along the eigenspace, A times V is just some constant multiplied by V, because it's keeping the same orientation, right? So anyway, that's the whatever. That's pretty much as geometric as it's going to get, right? It's pretty good, I think. I like this a lot, this website. Okay, what are eigenvalues good for, right? So they're good for doing very simple things, because if you take the matrix A and left multiply again and again by a vector V, then you get V, A times V, A times V, which is A squared times V, A cubed times V, and so on, right? So if this simply is the way to encode various discrete dynamical systems, right? So A represents, what happens to some state vector, and then you multiply it, you get the state of the system at the next time step, and then you multiply again, A doesn't change, so you get the state of the vector at the third time step. A lot of problems are in this class, right? Including how rabbits make babies using Fibonacci numbers are in this class, including Markov chains, which are basically, where when the matrix A is a whole bunch of non-negative numbers that sum to 1, right? And then your vector B is simply the probability of finding your system in a given state. So you have 3 states, like a frog jumping between a little, lily pad here, a lily pad there, and a lily pad here. It's a crazy frog. It just sort of goes and jumps, to one lily pad, and let's say there is a Toblerone bar it rolls, and with some probability, the bar lands, somewhere, and then it looks at the bar and says, oh, I have to go to this lily pad, so it'll jump, right? So let's imagine each lily pad has like a, 3-sided die, and those are the columns of this matrix, right? This is essentially a Markov chain, right? So it just kind of jumps around like crazy, and so the question is, what is the if you let the frog jump around like crazy for a long time, what's the probability we will find it, in one of the lily pads? So we go away, we come back at random after a long time. What's the chance? That's exactly the same idea, almost the same idea as the PageRank algorithm, right? PageRank algorithm is a little more subtle because, we want to allow for the possibility that there may be traps, right? Some lily pads. Now imagine each web page is a lily pad, like billions of them. And there can be traps. If the frog lands in one lily pad in some weird corner, it may never come out of it because there are no outgoing links to it, right? So then the idea these guys had, is that there's the Google founders, is that they said, well, at every lily pad, there is a little coin for heads or tails. So that comes up tails with probability 0.15, 15% of the time. The remaining 85% of the time, it comes up heads. If it comes up heads, then you simply choose one of the outgoing links uniformly at random from wherever you are and go there. If it comes up, heads, the remaining 15% of the time, then you choose any one of the web pages uniformly at random globally and jump there. That's called a random surfer model, right? So with small probability, this guy just goes anywhere with some chance, and then with most of the time, he just locally follows one of the things, right? That's just a technicality to get around what's called the irreducibility of a Markov chain. So this makes this Markov chain irreducible, which means you can go from any web page to any other web page because there's this small chance you can jump at random. So all these problems essentially become problems of this iterated system, A to the K times V, where K gets large. They're interested in that. And this is what eigenvalues let you do, because you can just take a V, so where you start initially, and multiply it by A, you go here, A square V, and so on. Eventually, it'll go into one of the eigenspaces, okay? And it'll start, converging to some point. That's very nice, right? So this is, so here's a concrete example with Fibonacci sequence. Say the number of adults at time t plus 1 is the number of adults at time t plus the children at time t, right? And the children at time t plus 1 is just the number of adults at time t. So every adult makes a child, okay, in the next time step. So this we can simply write as follows, right? This is your state vector v sub t plus 1, number of adults at time t plus 1, number of children at time t plus 1. And this is our matrix A, 1, 1, 1, 0. So if I multiply vt, adults at time t, and children, number of children at time t, by this, then the number of adults at t plus 1 is number of adults at time t plus number of children at time t, because children become adults in one generation in this model. And then number of children at time t plus 1 is simply the number of adults at time t, because every adult has a child. And of course, the children become adults. They don't make children right away. Right? It's a very simple model. And this actually is the Fibonacci sequence. So if you iterate this, and you start your initial condition with just one child, V0 is one child and 0 adults, right? Then you simply iterate it, and what you will get is actually the Fibonacci sequence. So let's just play this one time step. Next time step, you see, one adult made a baby, and there's one adult and one baby. Now there's two adults and one baby, because the baby became an adult, and okay, so you get the idea. So now you're going to converge on the eigenspace there, the eigenvector there. And so if you look at the lambda, the eigen, that's kind of cool, right? I think that's D3 maybe. Doesn't look like it. So anyway, lambda is 1 plus square root of 5 over 2. This is called is it the golden ratio or something? Yeah, no, yeah, golden ratio. Okay, so that's one simple example. This is again a Markov chain. It's a very, very simple two-state Markov chain, you know, East Coast and West Coast. So with a small fraction p, a fraction p of New Yorkers move to California, and a fraction q of Californians move to New York. Okay, so that's this and this. So the remaining guys stay put, right? They love their California or whatever their hometowns, home states. Now, so we can change the fractions and stuff. Let's just keep the default. So we can encode this as follows, right? This is essentially, exactly what happens. The number of New Yorkers at time t plus 1 is given by 1 minus p times the number of New Yorkers at time t, because they stay put. And then the number of Californians at time t with fraction q who come back to New York. So the first row gives us, those who stay and those who return. And the same on California, so the number of Californians at time t plus 1 again comes from those who stay in California times those who, leave from New York. Okay, so once you have this, we can play the same game and just let the thing mix. Of course, as soon as they reach California, they become black because they're Californians now. And as soon as they reach New York, they become... Okay, so this will stabilize, right? And you're seeing the state vectors V approaching some constant there. Okay, so now complex eigenvalues are the same story, except complex arithmetic is more beautiful. You already are doing arithmetic on the plane. You need notions of half rotations to make sense of complex multiplications, and see the usual multiplication by -1 as a 180-degree rotation from 0, 1 to 1, 0 real complex to -1, 0, right? And then if you stop a 90-degree rotation, you have the notion of complex multiplication and blah, blah, blah. But the high level, it just allows you to have more complex dynamics. So you can just look at this. So we have, it allows you to have, spirals. So you can start at some initial condition and for a fixed matrix with complex eigenvalues, oh, so I'm changing A now. Oh, wow, that's cool. All right, okay, you can play around, but kind of get the idea, right? So you can do quite a lot with matrix multiplications again and again by multiplying with the same matrix. Okay. So we already watched this, right, let me get back to our next guy in the list. So we already watched this video for Fika. So let's try to get into some stuff here. Yeah, this is just, so this, please watch on your own. I don't have time to show this. It's just recalling gradient descent and stochastic gradient descent, which I'll assume you know what it is. Okay, that's how we're going to do the optimization to find the best W for linear regression, or in cases where you penalize the model for its complexity, like ridge regression, or another more popular method called lasso. You throw in the penalty term, but in both cases you're usually doing gradient descent. Now I thought, instead of preparing all this, I thought let's just roll live. There is this blog update by Darren Wilkinson, this English statistician who's I mentioned earlier, and I thought we can kind of code at the same time because I haven't prepared for this. Okay, so the idea is to go in his research blog to the section called Analysis of Quantitative Data, and very quickly, for those of you who want to download Scala on your own machine and set up your system, just follow these instructions. If you're on, say, a standard Debian system like Linux, you have to work slightly harder if you're on Windows to figure out what to do. But sudo apt-get update, install OpenJDK 8, and then you can wget the full tarball of Hadoop. You might as well change this to 2.2, get the latest distribution. And then this is tar x is extract, v is verbose, output report, file is the target file, z is zip. So it's just going to extract the TGZ file and create a directory without the TGZ. So you can now cd change directory into that directory. And then there's another directory inside that called bin for binary files. So then you run the example called run example inside bin with this application, and you should get your little working example in your own machine if you want. So, try this on your own and do lots of Google searches before giving up if you get stuck. So this is essentially how you run Spark Shell locally. So, once you run Spark Shell, then you'll get an interactive REPL, I guess, which is Databricks is basically a souped up version of all of this, right? So we're just sort of sitting on a lot more than just the shell. Okay, so you can control, for example, the memory you're allocating to the driver and all sorts of things depending on resources you have. So a lot of that is taken care of you in the managed public cloud like Databricks, for example, and you can specify those options as well when you start your own cluster. Okay, so this is just quickly going through how to read a text file. So these things you can do in the shell as well. Creating an RDD, counting words in a file, stuff we did before. So try to follow this and do it in the shell. Reduce by key, blah, 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 word count. And now, this is what I want to do now. So analysis of quantitative data. So let's just sort of, so you guys know Breeze a little bit already, right? So he sort of wants to simulate some data using Breeze and then doing some simple stats on it. So I've not tried it. Let's see what happens. Just Control C. Right, so I'm creating some Gaussian sample. Seems to work. Good. Okay, so it seems to have created a vector, which is definitely not an RDD, so it's just a Scala collection. Let's see what Darren says here. Note that X is just a regular Breeze vector, a simple serial collection all stored in the random access memory on the master thread. Okay, so if you want to change it to RDD, we have to do this, val RDD sc.parallelize of X. So you guys know this command before, so let's do that next. Yeah. So I think let's just slightly jazz here. I think def makes it a call by, it's a lazy evaluation, so I don't get all that printout. Okay, it's a val. If I put def, it'll only get called when it has an action. Okay, so then let's see. Now XRDD is RDD, and so we can do spot transformations, blah, blah, blah. So now let's get XRDD. I have no idea if this will work, so let's try it. Okay, so I guess, yeah, so an RDD of type double has mean and sample variance. I guess I should do println maybe. Not sure. So I'm not sure why I'm only seeing the last one. Okay. Okay, so now let's see. Each summary statistic is computed with a single pass through the data, right? So when they ask mean, it's going to just run through the RDD, report the mean, and then variance is going to run through the RDD. Of course, if we know we want variance and the mean, then we might as well take advantage of a method that does a single pass and computes it. You know, these statistics, mean and variance, actually, Ronald Fisher, you know, the pipe smoker guy from the first lecture we talked about data science, he actually talked about these statistics and their special properties in the 20s. So they're called recursively computable statistics, which means as you go through a vector, a container, right? As you move through it, you can compute the mean by just updating one little buffer, right? You can compute the mean recursively. Variance also, you can compute it recursively. So it only needs to see the data once as it's passing through. So if there's special statistics. In contrast, you know, Fisher pointed out, median is not recursively computable. If you want to find the median of n points, right, you essentially have to sort them and then find the point kind of in the middle or between the two middle points, right? If there's an even number, or the middle point if there's an odd number of points. So that means you have to sort every time, which means as new data comes in, to find the median, you need to update your sort of everything up to now, right? Which is actually a global view. So that's not recursively computable. Median is not. These things matter later on if you know. Okay, so let's see. And then I think he just says, let's just, do this. So we do rdd.stats. It's called xstats. That's some method, stats counter methods. So it has all these things: count, mean, sum, max, min, and variance. So we can just do that. XRDD, I think all of this is good, so this should just work. Yeah. So it gives you all of this stuff at once. So now, what else? The regression. I mean, the idea here is that you should be able to do this on your own, right? So, so I don't want to magic here. Okay, so here, what is he trying to do? He's going to show us some linear regression. For that, he's going to simulate data, I believe. Start with some standard non-Spark Scalable code, simulate some data from simple linear regression model. Then we use X already simulated as a first covariate, blah, 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 simulate the second covariate, then use some residual noise, epsilon, and then simulate a regression model scenario where we know the true intercept is 1.5 and the true covariate regression, so on. Okay, so he's just basically putting this line with some intercept and some slope, and then throwing some Gaussian noise around that line, right? And then simulating from that and producing your X, Y coordinates. It's just simulating the scatter of points about some fixed known line, right? So that's all this is. So let's just try and grab this. Make sure we understand this. So let's yeah, so watch out. So this should be moved down. There's a problem with cells, guys. You sort of mix up the order. It's not good. Okay, so here, let's see. Let's comment Gaussian samples, 10,000 Gaussian samples, samples with mean 0.0 and standard deviation 1.0. I don't know if it's variance or standard deviation in the encoding, but it doesn't matter. Square root of 1 is 1. So, okay, so that's standard normal, I think, samples. So he's probably, now he's doing x with x2. What is x actually? X is the original thing, is it? Yeah. So x comes from 1 and 2, right? So mean 1 and variance 2. So he's now just zipping x with x2. Okay, so creating, I think they're tuples, right? So these should be 1,000 samples, right? 10,000 rather. Okay. And then he's taking XX, which is this pair, and then mapping every element P from that pair to this quantity, right? 2 times the first element, and then plus 1 times the second element, and then he's adding some intercept 1.5 to it. Okay, so yeah, so this basically will amount to our notation. It'll be x, so it'll be 2.0 times x plus 1.0 times x2 plus intercept 1.5, right? Sub I. $10,000, right? Oops. Okay, so that's basically what's going to happen. You're going to get a set of these points. So now he has EPS to be, again, some standard errors. And then Y is now LP, this line zipped with EPS, and this is the noise he's adding. So this will give you another pair now, right? Because this is now your, what is it called, LP. So LP sub I is now, oops, it's basically this thing, right? I'm going to say equal to, okay? Defined to be equal to, okay? So now he's zipping it with the EPS, and then simply, yeah, just keeping them as 2 separate points. And then now he's taking Y and zipping the Y with the double X, and then mapping it into 4 values now, P1, and then that's the first element of the tuple, and then this is the first element of the second element of the tuple, and the second element of the tuple. So this gives me Y, X, and so now he's turned that into RDD. Right. So this RDD, so to go downstairs because it's all vals, so it's evaluating everything by value. So okay, I'm going to do it this way. Control X. Control V. Can do show, right? Do take. Okay, so yeah, So I have a RDD of 3 doubles, and it's the X, Y, and the epsilon error, I guess. And then, so he simulated the data now. Right. 2 and 1. Now, note that the last line comes with this Scalable. We can in principle do regression modeling using more. Okay, so here, so he's taking this and converting to a data frame. Now that shows the first few rows of data frame, giving it a numeric argument. Okay, so this is, we don't need to get into the CSV. The data, okay, he's just saying if you read from CSV, it requires 2 passes through the data. If you don't specify the schema ahead of time, don't have to worry about it. Now let's get to this point. So he's going to do linear regression, I hope, with this stuff, with this simulated. Okay, so we have X, sorry, we have Y and the 2 coordinates X1 and X2 that cooked up in our simulation. Now let's get into linear regression. I hope we continue with DFLR here. Yeah, so let's see. Start by creating an object for fitting linear regression models. I'll just copy this into my buffer. So yeah, this is just creating, instantiating a new linear regression, and then, yeah, just explaining the parameters that are there. So there are many parameters, like the fitting, we'll do simple, no non-regularized ordinary least squares OLS. That's the first thing in Amit's video, just linear regression without any penalty. Assumes the data frame to be fit at least 2 columns, one called label, containing the response variables, and one called features, where each element is actually a vector of covariates. We already saw this, so we just have to take our DFLR, do this transformation where we map each row using this get double the first element, and then we're getting the double of the second element and the third element, and creating a dense vector, and then turning into a data frame with these names, label and features, right? So I'm going to be lazy, Control V this, and I will just copy this bit as well. Oops. See. Right, and now we have the data, then he's going to fit the model, right? Copy all this. So I'm teaching you how to copy stuff that's freely available and make a living teaching. I mean, I don't know if it'll work. Let's see. And I mainly want to do this so you feel like this is not a big deal, right? Because everything will change in a year, or a lot of things will change, and then you need to be able to do this on your own, right? So, okay, so basically that's it. So it looks like we fit the data. We found some, errors and residuals, and yeah. So Spark R and Spark has generalized linear models, so there's a lot more you can do with, if you know about GLMs, link functions, you can change from linear to logistic and a lot of other things. And we will get into cross-validation and stuff in our own pipeline soon. So let's just grab this, go downstairs, and thanks. Right, so we made the data frame. So let's do this piece by piece. Control X, do regression. Okay, so it's going to tell me all sorts of options. Now I want to transform the data like I want, because the machine learning library requires some format. I'm going to show it. Called it labels and features. It's all good. And we don't have to worry about casting it into a string or anything like that, because this is regression, so the labels are continuous. Now I'm fitting the model. Fit.intercept. Warning, a pure expression does nothing in statement position. You may be omitting necessary parentheses. Okay. Like this, maybe? No.
It's just that it's a pure expression, so as there are two expressions,
yeah,
it doesn't know which one to print, I think.
Oh, I see.
So just comment one of them.
Yeah, okay, fair enough. Yeah. Oh, I see. Oh, I see. Because it's, okay, yeah, that's Scala level. Okay, cool. Okay, so we have the coefficients that were fitted and the intercept, right? So now, let's see, this is a whole lot of stuff. Fit summary. I have no idea if this will all print. Let's try. Yeah, so I think you have to just do all of them separately. Is there a way to just pass this into a map it line by line? Anyway. Okay, so now I'm just getting the R-square error and so on and so forth, right? So you can do this one at a time. Okay, so the point is we just simulated some data and had x1 and x2, and then we sort of fixed some intercepts and got some errors and epsilon and created our sort of simulated data, and then we fit to that data. And we find that the best fitted values are sensible. They're close to what we used as our simulation. You agree? This kind of thing you have to do anyway, right? You're trying something out. You really need to make sure your algorithm functions properly as expected on purely simulated data. This is the first step. So this is a good exercise to do. Okay, so in the remaining time, yeah, you can get into this GLM stuff. I haven't really played with this yet. So now let's go back to our P. Where are we? Aha. So let's see. We'll do this. This is the video you already watched as well, distributed linear algebra. You can watch this later, but I'll quickly tell you. Remember, this is the communication hierarchy inside a cluster. So the communication time between the CPU and the random access memory is 50 gigabytes per second, whereas that between CPU and the disk is only 100 MB per second. Okay, and so there's there's a hierarchy in communication time, right? So you want to basically design, when we talk about distributed linear algebra, we are trying to design algorithms so that it takes advantage of this hierarchy, physical hierarchy we cannot change. Namely, it will try to minimize communication between CPU and disk and things like this. Okay, so this one I also recommend if you want to really be more serious into coding in this framework. So again, this is just a summary of it. And for sort of more mathematically inclined folks, there is a really interesting course on distributed algorithms and optimization from Stanford for graduate students. This course will be a really fun course to take. I mean, I printed out a lot of notes. I haven't done all the homework yet, but But, if you really want to understand how to make improvements on algorithms in Apache Spark, then the mathematical and algorithmic asymptotic details are in this course by Reza Zadeh. Okay, so that's just background. And what I have done here, okay, this is the ML programming guide. So maybe in the next 6 minutes or so, I will sort of crash dive into this. It's kind of there, so you can sort of flex your muscles on what local representation versus distributed representations are. And then we'll come back next week with the full machine learning pipeline for linear regression for the power plant example. Okay, so this is just, these links should work if you put the archives in the right place. So the first thing we'll do is local vectors versus, and then labeled points, local matrices, and then we'll get into the 3 types of distributed matrices. So local vectors you've already seen, right? So this is just local vector in Scala. So you can do, so there's the local vector. So you can import the MLlibs linear algebra package and call the vector or vectors, and then you can define these things. These are not the ones in Scala, but in MLlib. This creates a sparse vector, so we can say vectors.sparse, and then specify the dimension size and the index that's non-zero and the value that's non-zero. So this is standard. And you can also, specify sparse vectors this way. There's also Python stuff. It all works, I checked. So you can look at and see how to do the same in Python if you want to play with PySpark. Right? So the next thing we want is actually this thing here. Go back here. Label point. So remember, label points, you're already playing with them. They're the ones where you have a label and a vector for the features, right? This is essentially the input to lots of routines in MLlib. So a label point in Scala Spark, you basically import the linear algebra vectors from MLlib and the label point regression from MLlib, and you simply say label point to create it in the constructor here. So this is one is the label, and then you give the features which can be dense or sparse. So it's dense there, the features here, it's sparse. So for digit recognition, we already did this automatically, right? By loading it directly from this thing. So you can hand roll it like this. Okay, so this is just explaining stuff. Again, so again, MINAST, the same data set. We loaded it in Databricks Community Edition like this. So you can now explicitly say, I want examples to be RDD of labeled point. Okay, and then you can load it like that from the actual file, and then you can look at one element of it, and it's basically a MLlib regression label point. And the same with this one. So it's you can convert to a data frame and then display it, and this is exactly like we were doing in your notebook before. Right? It's your gray images, 780 pixel stuff. Okay. And this is literally the syntax from that notebook here, 016 notebook. So this works as well. Python is very similar, it's slightly different syntax. So you may want to dabble into Python sometimes, especially for TensorFlow or other things. Twitter, sometimes it's good to go to Python and come back to Scala. Because some libraries for Twitter are good in Python. Okay, it's just the same thing. And I'll just let you know there. So, and then local matrix. This is the one I want to spend like maybe the next 2 minutes in a big hurry. But here we have the various data types. So a distributed matrix can be either a row matrix, index row matrix, a coordinate matrix, or a block matrix. And Okay, so a local matrix in Scala, you already know all about it. It's just from Breeze, you already know, but if you want to import it from the linear algebra package in MLlib, then this is how you do it. Matrices dense and matrices sparse. You just pump in arrays with the dimensions. And here is, again, local matrix in Python. You can look at the syntax for it. So now to do distributed matrices, what you need to do is, so there's 3 types, right? So there is a paper that you may want to read. Where is that paper? Okay, I'll find the paper at some point. There should be a paper linked somewhere. We'll find it. Okay, so what's the idea in a row matrix? All right, maybe we'll stop. We'll continue next week. There's a lot going on. You need to understand this bit, okay, slowly. So we'll start next week. So are there any questions? I mean, this week I'm throwing a lot of information at you, but I just want to assume that everyone is on the same page about some things, okay? But please watch the gradient descent video on your own if you don't know anything about it, so you can assume some things. But yeah, the plan is quite straightforward from here. So we will basically revisit the pipelines, the power plant pipeline and maybe the diamond pipeline. We will do the pipelines with cross-validation for linear regression first. So the cross-validation part will, we'll have tuning parameters and things like this. So we'll automatically do all of that as part of the pipeline. And then we will eventually let random forests, so random forests or generalization of decision trees, will actually have, linear regression and random forests sort of fight out for best explanation. Right? So that'll give you a full-blown, end with model fitting, model tuning, and then we'll do that for a couple more examples. And finally, I'll start getting into Spark streaming, which is when data is streaming at you, and then you have to make decisions live and report back. This is deployment, predictions. It's called serving, model serving. You serve the predictions from your model live. For that, we will go back and spend a whole week on Spark streaming first, and then return back to the same pipeline, where now with your best fitted model, maybe the random forest or whatever, data is coming at you from the power plant, and then you're using Spark streaming to serve predictions live back from your fitted model. Okay.